All right, we're back again, and today I have a little calculus problem for electronics, which is pretty cool. It was just a problem I was working on the other day, and I thought, man, this would be great to share on the channel because it's a calculus problem that has to do with Ohm's law. It's pretty simple, but it has a couple unique things in it that I think are really tailored towards showing you why calculus is useful, and also just getting into revealing some things about mathematical thinking. You know, when we go through this problem, you'll see that there's some things in it that kind of show you like, oh wow, that wasn't that complicated, but it also, that was something I could have used my own reasoning to solve. Had I have looked at the problem in that way, it would have not been so intimidating to me. So this is basically a derivative problem. So we're going to look for the rate of change. Anything that has to do with the rate of change in calculus is going to be a derivative, okay? So what we're saying here is that we have a voltage. It says V increases at 6 volts per second, and I decreases at 1/4 amps per second. Okay, and we have a little drawing here of the circuit. So we just have an energy source, and it's just going to a resistor, and that's pretty much all we have. Okay, and there are some values that that are knowns that we're going to plug in here, because at the end, our end goal here is to find the rate of R. Notice I said the rate, not the value. Typically, when you have a problem like this and you see something like this in electronics, you're going to want to know what the value is, and you'll use some form of the equation V equals IR, which is Ohm's law. Okay. Now, if you want to know what R is, then you would take this and you would say R would equal V over I. And how I got that, if you remember about manipulating equations, this is something very simple too. If you're just doing like simple, like algebra based electronics, these are the kind of things that are going to help you. So again, you know, I'm trying to show things at the whole gamut over here. Some people might see this and say, I don't want to learn, I just want to learn basic electronics, and I don't want to, you know, fuss around with calculus. But there are some things that will help you, because calculus is based on algebra, okay? And you don't have to do derivatives every time you're trying to figure something out, but doing Ohm's law might help you figure something out, okay? So it's Ohm's law either way. So how do we get Ohm's law, for those that aren't familiar with it, so that you don't have to memorize all three of the equations? You only need one equation. For example, for myself, typically when I think of Ohm's law, all I think of is V equals IR, which is the voltage. That means voltage times current times voltage, or times resistance. So voltage equals current times resistance is what that's saying. Now, how do you solve for R? Well, you just do the inverse operation. So we see these two, I and R, are multiplied by each other. So what we do is the inverse, meaning we would divide by I on this side and divide by I on that side. That cancels out here, and we have V over I equals R, okay? And that's what R is. Now, if we wanted to say, what is I, get the third transformation of this equation, the third form of this equation would be, well, we're dividing by I, so now we're going to multiply by I. So if we multiply by I on both sides, I will cancel out. We're back to our original equation. And then I'm multiplying my R again. So I'll divide by R. Now I have V over R equals I. Okay, so this is your current equation for Ohm's law. This is going to be your voltage equation for Ohm's law. And then we have our resistance equation for Ohm's law. And that's how you would derive them just from one equation, right? Just from knowing one. So if you know one, you can know the others if you know how to manipulate them. So you don't have to try to remember V equals IR, R equals V over I equals V over R, that whole deal. You don't have to do all that. You can, if you know one, you can know how to derive the others. Is very useful. So that's the algebra lesson, and there's more algebra lessons in this, but that's a simple algebra lesson for somebody here who might feel as though they're not interested in the calculus. But as far as the calculus, again, part of why I'm sharing these videos is for people that are thinking about getting into engineering, or already in engineering, are in a degree program, or thinking about it, or they're wanting to learn more about how mathematics is applied to something like electrical engineering. Well, here are some basic examples. So again, we have V increases, and the reason why I brought that up again was because I was trying to make the delineation here. What I wanted to do is point out the delineation between how we usually see a problem like this and what the question is asking for. If we know V equals IR, like I just talked about, then we know that we can just get R if we use Ohm's law. You know, somebody that sees something like this would say, well, why are you making it so complicated? Why are we doing calculus and derivatives if we could just use V equals IR to find our own unknown resistive value, the value of the resistor? I could just find what's unknown by using this formula, basic algebra. Why do I need calculus? Well, you need calculus because this is now, the question is asking about the rates of change, right? The increase of the voltage, which is 6 volts per second, it increases, and the current decreases at 1/4 amps per second. And then we're asked to find the rate of R, not the value of R, but the rate of R. So the rate of this resistance when V is 32 volts and the current is 4 amps. Okay, so what we're going to do, we already have some knowns here. What we're going to do is see if we can derive some more knowns from this question here. We have to see what is V. It says V increases at 6 volts a second. What does that tell us? Does that tell us anything about our equation? Well, it does, but let me go further a little bit to show you what we're talking about and what the difference is here. Okay, so when I talk about this being algebra, this is algebra. You know how we take this from algebra and then turn it into calculus? Well, we do it in terms of describing this equation, this basic algebra equation, in terms of the rate of change with respect to what they're talking about in this problem. So what we're talking about is the rate of change in time, okay, in this problem, because it's asking about the voltage change and the amps current change and the resistive change over time. So because of that, that's going to influence us to want to put all of these values over dt, which is going to be the derivative of time. Okay, I'm going to show you how to do that in a second here. I just want to go over one thing. What kind of problem do we have here again? Can we see that this is multiplication? Yes, we can, because two variables put next to each other like this equals multiplication, right? That's a multiplication problem, so that means that we have a product. If again we know a little bit of calculus, then we know that we're going to use the product rule when we're trying to find a derivative of a product. Okay, but there's one stipulation here, is that we can't just use our regular product rule. What's the regular product rule? Now some people might write it differently. This is how I write it typically. So I have f prime of x times g of x plus f of x times g prime of x. Okay, but one thing you'll notice is that, again, if you're familiar, you cannot use this It's going to be very difficult to use this and confusing to use this because you can't differentiate the variables. Okay. So there's another formula that you're going to use to differentiate these variables. The other formula that you're going to use to differentiate these variables is d over dt. We're going to use dt because that's time and it relates to our question here. D over dt times u times v. Okay, and the reason why u and v are used is really unbeknownst to me. I think it's just it could vary. It's just some kind of convention that we're using here while we're doing this. It could very well be a and b. You can just think about it as a and v. It's just typically when this is talked about, they're using u and v instead of a and b. And you can see u and v and a and b are like very similar, right? They almost sound the same when you say them. So what this means, let me drag this over here. What this means, this is the product rule basically when you're going to, when you're doing a derivative of variables. Now how we do this is we're going to say du, this is what this equals, d over dt times u times v equals du over dt times v plus dv over dt times u. Okay, so the easiest way to remember this, it's not that hard, is just to remember that you multiply by the opposite. Okay, so if you have du, that means you multiply by v. If you have dv, you multiply by u, and then your bottom is constant because that's the whatever, you know, whatever metric that you're trying to use, whatever rate of change that you're after is going to be on the bottom in each case. Okay, so that's all you have to do is just keep track of the opposite. You just do the opposite variable. Okay, so a simple formula, but that's going to help us out and get us away from trying to use this. What we're going to do is we're going to use this formula here. But before we even get to that point, I'll show you why this formula is important, because we're going to take that formula and we're going to use that in our Ohm's law, right? Because this is algebra. This is Ohm's law in algebra. V equals IR. We're going to take V equals IR and turn that into calculus by doing the derivative of V over the derivative of time. So dV dt, okay, equals di, I'm going to do basically what I just have up here, equals, remember this is a product, so that means we're going to add it, so this is going to be di dt. Since this is I, I'm going to put r here, the opposite variable or the second variable that I have, plus dr dt times I. Now I've turned my algebraic equation into a calculus equation. Okay, now I've made it so that I have all these variables with respect to their rate of change with respect to time. Okay, so where do we go from here? Now we have to we just have to set this up to solve for r, and then we can find the value of r and the rate of change for r. But before we do that, let's kind of go back over the top and get our values, because some of this is already given to us, so we don't have to worry as if we have all these unknowns. So remember, V increases at 6 volts a second. So what does that tell us? That's already giving us a derivative. So when we look at this equation, dV over dt, well, dV over dt is in the question itself. dv increases. That's showing you a rate. It's showing you the rate of v. The rate of v is 6 volts a second. So the rate of v is 6. We can put 6. We don't have to put the volts. We just want to know the quantity. This is what I typically like to do. This is just how I do it. In terms of derivatives, if there's a derivative that I'm solving, I usually put it in the margin of the paper, and I'll put my other derivative. So let's see if we have another one. Yes, because we have another element element of the problem that is showing the change, which is di dt. So di dt equals the rate of change of the amperage or the current, which says it's decreasing. Now, the only thing I have to pay attention to is if it says it's decreasing, then we make it negative, okay? Which is negative, so negative 1/4, because it's decreasing 1/4. So that gives us two values here. Now, we could just plug the values in right now, but it would make it more messy to deal with. There's some interesting things in dealing with this problem that we're getting to, which is why I wanted to show you here. So let me see if I can zoom in here. Okay, so this is where the problem gets a little bit more interesting. So this is, again, we're doing calculus, but it's still using many elements of just basic algebra. So what are we doing now? We're just trying to solve for r. Now, can we remember where our variables are? Remember, this is v. Don't let all the other symbology, the variables, get in your way. This is just saying the derivative of v over time. This is still v, this is I, and this is r, okay? One thing to not get mixed up is this is I being multiplied by r, this is r being multiplied by I. That's not the primary variable. Another way to do this, I think, is a little bit safer. I don't get in the habit of it because I just know to look out for that, and I'm pretty cautious of it. But you could put a lowercase I if you wanted to, and a lowercase r, just to remind yourself that that's not the actual variable. You're multiplying by that variable, but this is the actual derivative that you're after, right? So that can be a little confusing. So we have that out of the way. So again, this is r, so this is going to be the variable that we're of interest. This is going to be the variable that we're trying to isolate. So if we're trying to isolate, what do we do? What do we always do in algebra, right? When we're trying to isolate a problem, that means we always try to get it by itself first, because now we have v, the derivative dv dt equals di dt plus dr dt, which is showing us what v would equal. We want to know what r would equal. So the way to do this is just like we do in algebra, is we try to get r by itself. And to do that, we would do the inverse operation of whatever di dt would be. So di dt is positive, that means we're going to make it negative, and that means we're going to put it on the other side, right? Basic stuff. Basic stuff, I was just doing this with some, 4th and 6th graders, right? Not calculus, but these same operations here. So r, I'm going to go back to using my capital R. I'm just more used to doing it that way. So it would confuse me if I didn't do it that way. So I'm going to do it that way. Equals, now I have my variable dr dt isolated. So now if the only thing is you just read this backwards, you say the derivative dr dt times I equals the derivative of I over dt times r minus dv dt, okay? It's helpful to read these things as sentences because that's what math is. It's all sentences. You should be able to read every math problem you have, and it makes sense to you. If it doesn't, then you need to figure out why. But all that should make sense to you. But now, does anybody see what's wrong with this sentence, in a sense? Remember, when we want to solve for a variable, we want to get that variable in its most simplest form. If we were to solve for this, then we would have what I times the derivative would equal. So we have to get this I away from this derivative. The way we do that, again, very basic operations. It's still the inverse operation, basic algebra. So I is being multiplied by the derivative of r dt. All we have to do is divide by I on both sides, and what we get is dv over dt minus r di dt equals, you can just take that away there, dr over dt. Okay, now we have our actual variable of interest completely isolated. But now there's one problem left. There's one problem left with this, and I wanted to show you guys this mostly because of what happens here at the end, because I think this is really going to illuminate a lot of your mathematical thinking. So, does anyone see a problem? There's still a problem here. We're trying to solve for the derivative of r, but we have r on this side here still. And we don't know what r is. Remember, r is our variable. We don't know the value of it, and we don't know the rate of change of it either. We don't know either of those things, you know. So how do we do that? A clever way of dealing with this is going back to what we did in the beginning. Remember we said V equals IR? If V equals IR, R equals V over I. Again, everything is a mathematical sentence. So when R equals V over I, that can also be read as V equals V over I equals R. Okay. So anytime you have I always call it like a, an equation of equivalence, right? Where you have a statement that says this equals that, you can read it both ways. That was Einstein's whole thing with E equals mc squared, right? You can read it both ways. So it meant that energy was tied to mass in some way and had to do with the speed of light. But that's a different topic. But if you read it in both ways, a lot of times equations can illuminate themselves to you in a much more vivid way. You can read it backwards because it means the same, that the relationship is the same. Sometimes you always get caught up in saying, oh, this equals that, but that also equals this, okay? So if R equals V over I, that means V over I equals R. So instead of using R down here, which is an unknown variable, we can plug in for what we know because we have V and we have I. So we can erase R and put in V over I. Okay? Now we can do the problem. And now we can see how simple this problem is going to be. Because we just had to set it up in this fashion, but we didn't really have to do that much. The reason why we don't have to do that much is what I'm going to show you. It's because now we have our variable isolated. We only have variables of knowns, things that we have information about that we can deal with. You call them knowns or givens, right? So here they are. Remember dv dt we decided was 6 because that's what our sentence told us in the beginning, minus V over I. V was given to us as 32 volts. So we write 32 over I, which is given to us as 4 amps, minus di over dt, which we read in our sentence was going to be a decreasing amount of amperage at a rate of 1/4. So that's going to be negative 1/4. Remember, that's all over. Don't forget you're all over I, which is going to be 4. Now that's going to equal R. Now you see that the math is very simple, right? The arithmetic is pretty simple. Okay, if you put that all into your calculator, you should get 2 ohms per second. That's the rate of change of this resistor when such a voltage is applied to it. I hope you found that interesting. Thanks for watching.